nanohub.org.
Online simulation and more for nanotechnology.
Okay, so good morning. We'll go ahead and get started. So we're really delighted to have Dr. Colin McAndrew with us this morning. So as many of you know, Colin is going to be holding a hands-on workshop on how to write compact models, beginning at noon and then through noon tomorrow. But he has agreed to begin by giving us a seminar on an important topic. Everyone is worried about uncertainty and variation in electronic devices and how that impacts design. So he's going to talk about the current work that he's doing that will be of great interest. Colin, I think you grew up in Australia,
Yep.
Is that right? Did your PhD at the University of Waterloo.
Yep.
And 1984.
Yep.
And I remember reading your papers on hydrodynamic flow equations about electrons and holes flowing through semiconductors. And then Colin spent several years at Bell Labs, where I believe you first became involved with compact modeling.
Yep, that's right.
And since 1995, he's been at Motorola, which is now Freescale. He's a leading figure in this field of compact modeling. It's true. And he's been very generous, with his time in terms of helping the community, helping students and engineers learn the art and practice of compact modeling. He's a technical fellow at Freescale. He's a fellow of the IEEE. He's a former editor of the Transaction Electron Devices. He's been on numerous program committees. We're really fortunate that he's on the Industrial Advisory Board of the NEEDS program. So it's just a real pleasure to have you here with us. He came from Arizona and without a heavy coat. He said living in Phoenix, he will never again complain about it being too cold. But we'll see after a couple of days what you say about that. But welcome to Purdue. We're looking forward to your seminar.
Okay, thank you, Mark. It's a pleasure to be here. So what I'm going to be talking to you about for the next hour is about statistical modeling for semiconductor devices for circuit simulation. So it may look a little bit esoteric, but this is our standard practice within our company for how we actually determine the statistical models. We have two general purpose programs for doing the statistical modeling that I'm the person that wrote. One of them characterizes global variation, which is the overall variation of parameters, and the other characterizes differential performance between two devices, which is mismatch. And I'm not really going to talk much about mismatch today, but the theory behind the modeling for that is identical to what's here. I'm going to give a quick introduction to where device variations come from, some comments about statistical modeling, the basis that we use for it, and I'll go through an example of how you can actually model correlations by using uncorrelated variables, and we use this all the time. Then I'm going to go through the details of what we call the BPV, or backward propagation of variance procedure. So it's general. I'll go through the details, requirements, and only one example. So I've been doing this for about 20 years, and we've applied it to all sorts of devices, and it basically always works. And so it doesn't work under three conditions, and they are problems with the inputs rather than with the way the procedure works. I will then go through some details about corner models, which is another way of doing statistical simulations, and show that there are some significant problems with those, particularly for analog circuits. Throughout this talk, a P sub I is going to be a process parameter, which is going to be something like a substrate doping, or a delta L, or an oxide thickness. And EM is an electrical performance. It can be anything. It could be a VT for a transistor. It could be a current. It could be a GM. It could be a ring oscillator delay. It could be anything for any device or circuit. But that's the nomenclature that I will use. So what do you need to do in statistical modeling? What I'm showing here, this is from a half micron technology, and I'll use this data set for some of the examples here for two reasons. One of them is because I have tens of thousands of data points from this technology, and secondly, because it's a half micron, it's not affected by local variations, which is mismatch. The microscopic fluctuations show it better highlights the way that the global characterization gets done. What's being shown here in the vertical axis is the saturated drain current of a PMOS device versus the saturated drain current of an NMOS device. So in models, we need to do four things actually. We need to be able to model the limits, and we'll use that for corner files. You need to be able to model the distributions, which is then used for Monte Carlo type simulations. it's very important to model the correlation structure, which is one of the reasons why mostly today I'll be showing you bivariate plots. Often people would just look at a histogram of one parameter, but in particular, when you're looking at correlated device performances that affect circuit performances, which the ID sats of NMOS and PMOS do, it's important to get the correlation structure correct. And there is mismatch, and as I said, I'm not going to be talking about that today. This is a set of data to show you what the correlation structure can look like in real data. This is from a 130 nanometer process, and what's being shown here, the length is increasing. So this is L of 0.15, 0.3, and 25, and here the width is increasing. So we're going from small here to big here. And what's being plotted here is the threshold voltage of one NMOS transistor versus the threshold voltage of an adjacent transistor that's placed next to it and laid out identically. And there are data here from 17 manufacturing lots. It's a little hard to see here, but each symbol is from a different manufacturing lot. Because the threshold voltage varies with geometry, the absolute values of the axes are different, but the range of the vertical and horizontal axes is the same for all of those plots. And what you can see is that the structure of that data changes. And in particular, if you look at the big device and the top right and the small device in the bottom left, you can see that there's some difference. This is those data plotted on the same scale. So you can see that there's a difference in the spread of the data and there's a difference in the magnitude of the variation in the data. The colours and symbols there represent different lots. It's a little easier to look at here. What each separate colour and symbol is here is from a separate wafer lot. So there were 17, and I've deliberately chosen the 4 wafer lots that, for the wide long device on the left, have the greatest spread in them. So you can see that there's a significant variation here, and there's essentially almost a linear correlation between those. And what that indicates is that the threshold voltages are moving together. So variations are correlated, and it's coming from global process variation, which is the overall variation in quantities like the substrate doping and the oxide thickness between wafers, between lots, and it could be between manufacturing sites, but here it's just between lots. They were manufactured in the same plant. On the right-hand side, you can see that although those purple triangles are somewhat distinct from the red triangles, basically the clouds of data from each of these is merged, and you can see that there's an much more uncorrelated structure to these data. And that's really the transition here from being dominated by global variation in parameters to being dominated by local variation parameters, which is mismatch. And these are things that we have to worry about when we're generating the compact models. So how do we set up the models for these for running simulations? I'm going to show you here an absolute variation which is additive because it's simpler to understand. Normally we work in relative variations, percentage variations. So each parameter is modeled with a nominal value, and then there's a number of standard deviations of global variation multiplied by the sigma of the global variation. And there's a number of sigmas of mismatch standard deviation multiplied by the sigma of the mismatch standard deviation, which is a function of geometry. And as I've just shown you, the smaller you get, the bigger that variation gets. So this quantity here varies in generally reciprocally with the area of the device, or the square root of the area of the device. So the key things here are that we've separated it to a number of sigma times the sigma. If it was a relative contribution, it would be multiplied by 1 plus this quantity, but it's easier to show the absolute variation. And so essentially by partitioning or characterizing separately the amount of local variation and global variation, we can capture the correlation structure between two similar devices. It turns out very easily, that's not what I wanted to do. Sorry about that. It turns out that once we've characterized the sigmas, and I'll be spending a lot of time showing you how we actually calculate that standard deviation, that it becomes very easy to set corners because you just do those by defining a number of standard deviations of variation. There's some significant tricks in how that number gets determined, But it turns out then that for perturbations for corners, all we have to do is to vary that one parameter. And if we want to do a Monte Carlo simulation including mismatch, all we have to do is generate statistical samples for the number of sigmas of global variation, which is done once per device type. So if I have 100 NMOS in my circuit, I generate one of these for each parameter that I'm varying. And for mismatch, it's local to a device. It's uncorrelated between the two devices. And so one of these gets generated for each parameter for every instance of a device that's in your circuit. So we can set corners with the NSIGs, and we can set Monte Carlo simulations by just generating random values for the number of sigmas of variation. And the interesting thing about that, or the good thing about it, is because we're varying the numbers from -3 to +3, it has good numerical scaling. And for as long as, for example, if the variation in a lateral geometry, which is what we use for absolute values, we use in microns, so you get numbers around 1. And for relative contributions, they're always in percent, so that's okay. So this is the basis, the modelling basis that we use. And what later I'll show you on is how we characterize both the NSIGs and the sigmas. And again, I will not really be talking about that component too much. So this is a chart that tries to show you what the structure of the variation is. And this is a plot that several people I've seen use, and they always get it wrong, okay? What I'm trying to show here in green is the global variation, and that's here I've got P1 and P2, and I'm trying to show, for example, a 3 sigma yield ellipse from this with the green ellipse here. And then on top of that, I add the local variation, which can be smaller or larger for bigger devices. On the left, this is for a physically larger geometry device or a device in an older technology. And the amount of local variation is small compared to the global variation. As the geometry shrinks and as we get to finer and finer line geometry technologies, the amount of local variation gets significantly larger. And the error that you will always see in people when they show this chart is when I'm looking at the total variation, which is the blue ellipse, they will make it line up with the perimeters of the purple ellipses here, okay? And the cardinal rule that you must always remember about adding standard deviations is that you can't. You always add variances, you don't add standard deviations. So the total sigma is the square root of the sum of the squares of the variances, which is less than the sum of the standard deviations. And one of the techniques that people use to try and quickly characterize the effect of mismatch is they will select a corner, which would be an extreme value for a parameter here, and they'll do a mismatch simulation on top of it, and that would predict the variation for the whole circuit would be at this point, whereas in fact it should be at this point. And the mistake there is that they're mentally adding standard deviations rather than adding variances. So I think that's a nice depiction of how the structure of the variation is changing, but a lot of people make the mistake about adding standard deviations rather than adding variances. The parameter basis that we use for statistical modelling, always it's better to work in uncorrelated variables. So if we're looking at a MOSFET, you might use a model that has threshold voltage VTO, the body effect coefficient gamma, the gain coefficient K prime as variables, and often models are constructed on these. But these quantities all depend on the oxide thickness and the substrate doping. So there's a degree of correlation between these. It's much better to use flat band voltage, oxide thickness, substrate doping, and mobility. And really, the mobility should depend on the substrate doping. So there's not a complete independence here, but there's a little bit of hiding some things under the hood. In practice, it turns out to work fine, but you really should use these uncorrelated parameters. For MOSFETs, that's generally reasonable. The tricky one is bipolars, which I won't cover here, which aren't constructed from physical mappings from process parameters, so you have to add those. The good thing is that they were defined by a person whose job I actually took when he retired at Motorola in 1989, and to this day we still use the same mappings. What I've found is that whenever there's been anomalous variation in statistical variation over geometry or bias, by basing it on these physical parameters, we have always been able to explain that. And then those correlations that I said are important, we automatically get those between the model parameters because they come from the mapping from quantities like these to quantity like these. Again, more important for bipolars. And between the electrical performances of the device because they come through the SPICE model. Now, what is a statistical model? And it turns out there really is no such thing as a statistical model. There are statistical simulation techniques, and each of those simulation techniques requires a different type of statistical model. Corner simulations have been the mainstay of the industry for many years and are still quite reasonable for digital CMOS, but there are a lot of issues with those which I'll show you later. They require case files, corner models. Monte Carlo simulations require distributional models because you're generating distributions when you run the simulations. Obviously, you need mismatch models for mismatch analysis. And one of the best things that you can do is sensitivity analysis, but you really need to have that physical basis for the models to be able to do that properly. And I'll make one comment here. I'm putting sigmas down, but we never actually know what the sigmas are. By definition, you don't know what the true capability of a process is until it's after it's been in high volume manufacturing for quite a few parts. And at that time, you needed those models 2 years ago to be able to do that design. So in fact, I many years ago came to the realization that we don't get manufacturing data and generate a sigma from it. What we do is we use that data early on to come up with a specification for the variation for the process, and then we align manufacturing to that window, and we align the models to that window, and then the models will represent the manufacturing process. So that sigma actually comes from engineers understanding what's needed and understanding what's changed in the process. So I will represent it as a sigma, but it's really a specification that then we will treat as plus or minus 3 sigma values. So how do we model correlations and how can we actually extract that? And it turns out to be fairly straightforward, and it turns out to be rather slick, which is why I'm going to show you this example. So this is how we can model correlations using uncorrelated parameters. We'll show it to you as a analytic example, and when we use it in practice, it's actually done through a set of tools that I generated that fit the correlations, but it doesn't do it analytically like this, but it's fairly easy to understand. What I'm showing here is the L effective of a PMOS transistor versus the L effective of an NMOS transistor. So clearly you can see there's some correlation there, but it's not perfect. So what's the source of that variation? Well, there are 2 things that you can think of that come into that variation, one of which is the poly CD. So the sizing of the poly, which comes from the deposition and etch steps, is common between the NMOS and the PMOS, so you'd expect that to be common between them. But then there are out diffusions of junctions, and they're done with different implants and at different anneals, so that we can consider that they are, to first order, that they are uncorrelated between the devices. And so then we can model the delta L, the difference between the drawn or the effective or the design length and the effective electrical length, as the CD variation plus the out diffusion for the P for the PMOS, and the CD variation and the out diffusion N for the NMOS. So now we've got 2 quantities, L effective N and L effective P, and we've got 3 parameters. And so how can we actually characterize these? This seems counterintuitive, but what you do is you take the difference between them, okay, which is the delta. Now, you'd think that I've got a measurement of L effective P, a measurement of L effective N. If I take the difference between them, I don't really get any new data, okay? It turns out statistically, though, there is. So let's look at, in a matrix form, what happens then when I want to have these 3 parameters, ODP, ODN, and CD, map into those 3 delta parameters. And you can see that this matrix is singular, right? If I take this row and subtract this row, I get this row. So that matrix is singular, and I can't solve that on any individual case. But when I look at the way that the variances propagate, the key thing here is that when you propagate variances, you take the squares of the coefficients rather than the coefficients themselves. So when you add variances, it's the square of the coefficient times the variance. So what happens is that -1 becomes squared, and in fact, that matrix then becomes non-singular, and you can uniquely solve for that. So you can directly solve for it, and it looks like it's a bit of magic, but what's really going on is that there is the third piece of information in there. Because we're looking at the statistics of it, I don't just have in the data the variation, the sigma for the LN, the sigma for the LP, I also have the correlation coefficient. So it turns out that there actually is a third piece of information there, which is the correlation coefficient. So this is analytically calculated values for the ODP, ODN and CD using that matrix equation that I just showed you. I ran a 10,000 sample Monte Carlo, and these are the 1, 2 and 3 sigma yield ellipses that were then computed from that. So here what I've done then is I've taken uncorrelated variables, and by mixing and matching them, and I've then made a model of the L effective variation that properly captures not just the distributions but the correlations. So the key thing is that you can always, I've always been able to, I guess I can't say that you can always, get away from having to include correlations in between model parameters by formulating them properly and then making the right measurements to be able to untangle what are the things that cause the statistical variations. And I did this about 10 or 15 years ago when I was just about getting ready to add a capability to explicitly handle correlations into our statistical characterization program. And then I realized you actually didn't need to do it. You can always model the correlations through an appropriate set of uncorrelated variables. So what do we really want to do in device models? Okay, this was a thing that started me down the track to this procedure that I'll show you. This is from a guy that used to be my 2-level up boss at AT&T. And what this is showing, this is an end threshold voltage and a pre-threshold voltage. The symbols are manufacturing data. The square is manufacturing specification. And where the models are actually the corner of the hexagon there. It's a little hard to see. I'm actually going to put up 2 hexagons now. So we actually used to have 2 separate models for the process. One of them was model A, which was the analog model, and one of them was model D, which was the digital model. And those models never exactly agreed because obviously they were different. So when we extracted those parameters for those models from the same data, we got different values for the particular corner cases when we ran the simulations. And what used to happen was that every month we had a meeting between modelling, technology, development, manufacturing and circuit design, and would put up plots like these to understand that the models were representing the process correctly and the process was in control. Okay? And every month I got sick and tired of having to explain why those 2 models were different, right? So, well, we know that the core equations are different, and we know that when you fit data, the model parameters are going to be different. So when you get predictions of what should happen at the corners, there's some errors in them, so it's going to be different. But, you know, what I really wanted to do was not to have to waste half an hour each month explaining that. So the simplest way to do that is to force fit the corner models for each of those, or the corner values for each of those models, so that they perfectly fitted within that manufacturing box. And that's where the genesis of the procedure that I'm going to show you comes from. So that's sort of the basis for how things happened and what we use as statistical modelling basis, how you can model correlations. I'm quickly going to explain what's a common, although getting less common way of doing the statistical modelling, and then I'll show you how to do it properly. So forward propagation of variation is basically what you do when you directly measure those parameters in manufacturing. So you'll measure a delta L, you'll measure a T-ox, you'll measure a substrate doping in some way, typically from the body effect. You'll measure some quantities, a peak GM from which you'll calculate the mobility, and then you'll take those numbers and you'll stick them in as the distributions in the models. This is a good thing because you do get the distributional value, the distributional models for it, and you can get corner models, which, as I'll show later, are typically defined as plus or minus 3 sigma in those parameters, which is the wrong way to do it. But there are a whole lot of issues with that. You can't measure the P directly. You know, an important thing for a bipolar is the collector resistance, but it's very, very difficult to measure. So you do it on a test structure that then you typically have a different biasing configuration or a different geometry from what you use in a real device in a real circuit. So that's fine for getting the parameter, but what's the point of doing simulations for circuits? It's to simulate circuit performances. I don't really care what the parameter values are. So if I get the parameter from a very, very different measurement than condition that I'm going to use in practice, that's not a good thing. For example, modelling people, when we measure MOSFETs, we like to measure at very low VD because it gets rid of the effect of velocity saturation and dipole and channel length modulation. So we do that to get the parameter values. But if you're in an analog amplifier, you're going to be operating that device at a large VD in saturation every time. So it's a very, very different biasing configuration. So if the model's not perfect, I might have fitted the parameter in one region, but then I use the model in another region, and so the prediction of the window, the spread for that parameter is not necessarily accurate. There's 100 different ways that you can measure L effective, and they all give you a different value. And then if I take the different values, the different spreads, and feed them from the same model, I get a different prediction in the variation of the ID-sats of the transistors. But I know that the ID-sat variation should be fixed, so that's wrong. Oops, sorry. If I use the same variation in different models, the models are different, so I get different predictions. And as I said before, we had an analog and a digital model, and still to this day we do that. We typically use BSIM4 for digital and PSP for analog. And the models are different, so if I predict different distributions in the electrical performances, that's not what I want to do. The variations in the electrical performances depends on the number of parameters, and I'll show you that later on. And the main thing is there's no accounting for the sensitivity. I'll say this again and again. So if I go in the corner models and put fixed variations in the delta P's, then given that the sensitivities change with each circuit, each geometry, each bias that I have in the transistors, I get different predictions for what the variability of the circuit performances are. So it looks good. This was used 20 years ago, but there are some big issues with this. What it's really doing is it takes a parameter distribution, and if I have two different models, ASIM and ZSIM, and I predict electrical performance distributions, I get different values out, which is not what I want to do, right? I really want to fit these, and I want to get these such that I fit these properly. So that's where backward propagation of variation comes in. And the backward is because instead of going this way, we go this way. So it's really rather simple. It's based on the observation that I don't really care what the parameter values are. I care what the electrical performances are that's going to affect the behavior of the circuits, because that's what I want to predict in simulation. So using a simple sensitivity analysis, if the value for some electrical performance is its value for the nominal parameters plus the sum of the sensitivities times the variations in the parameters, then standard analysis tells me that the mean value of these is the value for the mean of the parameters, and more importantly, remember I said that you add variances and you add them with the squares of the sensitivities. So the variance in any parameter is the sum of the sensitivity squared times the variances of the input parameters. And I've dropped the pi here, it's just I, because it makes the notation a little simple. It also turns out that you can calculate the correlations in this form as well. So what I really have now is that I have a set of equations that I think I should be able to solve to give me what the variations in the electrical performances are. Because this is really a matrix equation. I'll show you an example in a minute. I'm going to ignore this for now. And this is I make a sequence of measurements, and that gives me a sequences of measured variances in threshold voltage for a wide long, threshold voltage for a wide short transistor, peak GM for a long transistor, ID-sat for a short transistor, and I'll explain why we choose those. And then I've got sensitivity squared, which I can calculate, and I'll tell you that in a minute. And then I've got a sequence of unknowns, which is the variations in the parameters. So that gives me a set of linear equations that I can just directly solve to give the variations. This is that set of equations for a MOSFET. So this is the variances in the electrical performances. The R here is a reference. The subscript R is a reference, which means wide long, and S is short, which is a wide short. You'll notice that the beta here is the gain factor. This is the threshold of the wide long, threshold of the wide short. This is the gain factor, and this is the saturated drain current. And here I've got a relative variation instead of an absolute variation. And then this is that matrix of squared sensitivities, and this is the matrix of the parameters. You'll notice that there's 4 of these, and there's 5 of these. And the reason for that is that often there's a separate test structure for TOX, so we actually do typically directly get a measurement for that. And then what I can do is by multiplying that by the appropriate column in that matrix and moving it to the left-hand side, I can subtract that variance off from the measured variances or specified. Remember, there's specified variances in these quantities, and that gives me a set of linear equations that I can solve for the sigmas that I want here. Okay, and it turns out that in practice you can work out up front what many of these things should be. Here, this is the wide-long threshold voltage. It's not going to depend on mobility. It's not going to depend on delta L. It's not going to depend on, this is sort of an empirical variation in threshold for a short device. So that should be a 1. The beta of the wide-long transistor doesn't depend on threshold voltage. It should have a 1-to-1 relationship to mobility, which is that one there. It shouldn't depend on anything to do with short channel. So you can actually look at this set of matrix equations and you can work out up front what it should be. But that's sort of it in a nutshell. That's how the procedure works. And then we generate these things based on engineering understanding and manufacturing data, and then we calculate what those sigmas are, and that gives us the sigma values. So basically what we're doing is we're taking the results that we want and we're force-fitting the variations in the parameters to give us those results. So the total procedure for generating the statistical models is then this. So we get the mean, variance and correlation, although I didn't show that there, of the electrical performances from the manufacturing data. Use engineering knowledge to come up to a set of specifications from that. We then use simple least squares optimization to tune the nominal values of the parameters such that we hit the nominal values of the electrical performances. The sensitivities then are computed from the SPICE models, and this is done separately for different models. So when we support BSIM4 and PSP, we actually will run this twice. And there's an automated program that runs what I'm showing here. It takes about 5 minutes to generate a set of statistical models. The BPV equations, which are those equations, are then solved for the variances of P, and I showed you how you can include an FPV parameter. And the corners are then specified in terms of the electrical performances, not the parameters. And the n-sigs, the number of standard deviations of global variation, are then determined by least squares optimization to fit the specified values of E, which we get from looking at the extremes of manufacturing data.
Question.
Yes?
So you said early on you don't have the manufacturing data to do this. That's step 1.
Yes. We don't have the manufacturing data, but we don't just generate those specs based on expectations for the process. So as the process is ramping up, typically there's a staged set of releases of models. There's, there'll be a set of paper models based on the previous technology, a maturity technology level 0, 1, 2, and 3. We get better and better data for those. And so there is some data, typically never from 2 years of manufacturing, but from running the lots that bring up the process, we do get data for, that factors in to generating the specification. So, and often early on, if we get the first few lots for it, the technique that we typically use is if you generate a set of models, you never ever want to widen the window later on. Because if you do, if early on someone has designed some circuit blocks based on this window and then it opens up, that means it's not going to yield or it's not going to work then. And no one ever goes back and redesigns circuit blocks. So if we start with a window that's deliberately made a little big and then try and make sure that we narrow it down over time, even with mean adjustments, it means that anything that was previously designed will still continue to run. So the manufacturing data is an input, and then thought goes into generating that. So I've shown this to lots of people, and everyone thinks it looks hopelessly complex. It's really, really difficult when you first are shown it to actually understand how it works. The math in those equations scare engineers. If they've been away from school for 15 years, they've sort of forgotten that. It scares people. It really does. But it's really, really, really simple. And a lot of people, when they take the time to do it, the penny finally drops. And I've had so many people say to me, you know what? It's really fairly simple. And then they adopt it and use it. Infineon uses this procedure to generate statistics for their whole process at once. They take every single one of their SGPC fab measurements and they run it through that procedure. And it works fine. So it's really simple because it's almost cheating, right? Because what I've said is I want the variations in E, and what I'm doing is basically calculating the variations in P to give me the variations in E that I want. And it just happens to be an iterative process that does it. There's a direct calculation that I've shown you. It actually is done iteratively. It takes a few times to get results. I won't go into why. And again, remember that I don't really care what the parameters are. The models are an approximation. The way I measure the parameters, if I did measure them directly, is imprecise. What is important are the electrical performances, and if I choose those so that they are the key things that affect circuit performance, then basically by definition I've got a set of models that should represent manufacturing accurately for generating.
But you want this model, these model parameters P, to be very physical.
Yes.
You want to go back to the manufacturing person and say, I need better control of this P.
Yeah, the manufacturing people know what to do anyway. I don't think we've ever fed anything back from a set of models to them. We do use these to understand where circuit sensitivities are. If a part fails or over years all of a sudden the yield drops out, we'll do that. But the fab engineers know what knobs to check. They have their metrics and track them. So I guess I've never seen it used for actually manufacturing control. It's really to get the models right for simulation. So here's the tricky bits then. That process fails miserably under 3 conditions. So the first are if there are inconsistencies in the variations that you put in. If you remember the example with the variances where I had a variance of a beta and I'm subtracting off basically the variance of the TOX from that. Now if I look at a wide long device, they're essentially 1-to-1. When I look at the variance of the peak GM of a wide long transistor, it's in a relative sense, it has 2 sources, the TOX variation and the mobility variation. And I add variances. Therefore, the variation in the peak GM must be greater than the variation in the oxide thickness. This is the greatest source of issues with that procedure running. Because this is no longer true because fab control of TOX is tightened up. But up until probably certainly quarter micron level, every fab engineer that I ever asked, when I said, what's the 3 sigma variation in TOX, they always said plus or minus 10%, right? Always. And it was always better than that. It always was much tighter than that. When I'd ask them, what was the variation in a peak GM, plus or minus 3 sigma, they'd always tell me from the data, it looks like it's plus or minus 5%, plus or minus 6%. So how can something that depends on A and B, then if A has a variation like this, how can you tell me that the total variation is less than that? So these inconsistencies are the number one cause of issues. And all it means is you have to make sure that the variations that you're telling the program to fit have to be sane and rational. Issues with the SPICE models are a problem. This happens very occasionally. If the sensitivities are messed up, if one of the SPICE models isn't working properly, then you get an issue. And the other thing is if you don't make the measurements correctly. If you don't, in fact, what has to happen is that the parameters that you vary have to be mathematically observable in the electrical performances that you measure. And if that's not true, then you have no visibility into what the variations of the parameters are. And I've seen this happen once, and once only in 20 years. So I think that it can be frustrating. Let me say it can be frustrating when this happens. And we have to go and look at those matrices that the program prints out, the sensitivity matrices, and it can be frustrating, but it's a very good thing because it means it's not a garbage in, garbage out process, okay? You can't just generate junk models. If you give it junk input, the process doesn't work. So it means that you have to make sure that your measurements are okay, that the specifications for the variations are okay, and that the SPICE models are okay. And if you do that, then everything works fine. And again, I haven't specified what type of variances are. So I said that this works for mismatch, the local variation, as well as the global variation for the parameters, but I'm not going to go into that. So let me show you an example. This is for PSP, and this includes correlation. So it turns out that PSP has separate out diffusion and poly CD parameters. So we just link the ones between the N and the PMOS. Threshold voltage depends on flat band oxide thickness and substrate doping. The body effect depends on TOX and the substrate doping. So what we do is we separate VFB and N sub for the NMOS and PMOS, and then keep TOX in common between them. TOX control is very good these days. And then we include the correlation and the body effect and its correlation between the PMOS and the NMOS devices fitting quantities. So what this is doing is instead of having an analytical solution for the correlation like I did before, and you can actually do it for the body effect, it actually comes through the numerical program. And so that means that we can get the statistics of TOX only from DC data, which is very interesting because normally you can't get TOX just from DC measurements because it's confounded. It depends on the oxide thickness and the substrate doping, and you typically can't separate those from the body effect. You can't get it, but when you look at the statistics like I'd shown you before, you can actually do that. So this is, these values are normalized. This is the PMOS versus the NMOS threshold voltages, and they're actually not that correlated, but the TOX extraction was the thing that gets the proper correlation in the model for that. This is fitting of the saturated current for the PMOS versus the saturated NMOS without including explicit fitting of the IDSAT variation. Remember we did that before by having the out diffusion N, out diffusion P and CD. So that's done here, but they're not fitted analytically. What we do is fit the correlation in the data, and you can see it fits it really quite well. So I'm now going to flip topics a little bit and look at corner models. And I'd like to show you what the biggest problem with corner models are, because this is incredibly misunderstood. So let's look at what corner models do for MOSFETs. And as I've said before, what I've shown you now with the BPV was for the sigmas. So that's used in Monte Carlo simulation. Now we're looking at discrete simulations of what should be the corners of the process. So this has historically been driven by digital. We want to bracket digital gate delay, dVdt equals I on C. So you get I variation and C variation, and you get digital gate variation. Two other key things that are important for digital circuits are the power and the leakage, but it turns out they're highly correlated with the delay. Anytime you sort of have fast transistors, then you've got higher currents and you've got higher leakage. So even though there's three things that are important, they're highly correlated, so there's really only one thing. Digital circuits also have the same look and feel. They've got pull down NMOS and pull up PMOS devices. They use minimum channel length devices, so you're not sensitive to things that vary with length too much. So the strategy used to be simple. This is an oversimplified way of presenting it, but basically for the best case models, which means you've got highest current, you make oxide thickness thin, you make channel length short, you make threshold voltage low, and it's done with 3 sigma. And for the worst case models, you just flip around the sign of the sigma variation. So simple, and many models that you get these days are still done that way. But what's the issue with it? Well, the fundamental issue is, remember we had the sensitivity relationship before? So the variation in electrical performance is the sum of the sensitivities times the variation in the process parameters. But for corner models, the delta P's are fixed. And so the variation that I get in EM depends on what the sensitivities are. And those sensitivities, they vary with the sort of performance that I'm looking at. They vary with geometry. If I have a long transistor, I don't care what the delta L variation is. If I have a short transistor, delta L can be the key parameter that I want. They can vary with bias. If My gate overdrive, VG minus VT, is large. I'm not that sensitive to VT variations. If I'm really close to threshold voltage, I'm very sensitive to VT variations. So these things vary all over the place, and consequently, corners guarantee absolutely nothing about what the variations in electrical performances are. So what's the issue with that? So the answer is, for digital, not much, because that's where the methodology came from, and for the reasons I've given before, the performances that you're concerned about are correlated, the circuits are simulated, so it works fine. And for analog, the answer is it depends. This is the problem, because you can't categorically say what's going on. Those sensitivities vary with everything, as I've shown you, so that the corner models really shouldn't work for analog. Now, everyone knows that, but the actual data that shows this is very rare on the ground. The first presentation that actually showed this was from John Crick from TI, and it was wonderful. It was at an ICCAD workshop in 2008, and I was a presenter there, so I got copies of the slides and got to see it. But this was never published, and so the world at large really didn't know about it. And so I got sick internally of explaining this to designers again and again and again and again and again. And I would always swipe his slides. With attribution, I always had the attribution there, but I really wanted to have a publicly available set of results that showed that. So this is where this analysis comes from. So working with some designers in 90 nanometer CMOS, we got a CMOS op-amp that's not really that complex, and we ran multiple types of simulations. It had MOSFETs, capacitors and resistors, and when I combined all those corners, there were 81. I ran, I'm going to look at the results from all of those and just the MOS corners, and then I did 1,000 sample Monte Carlo with global only variation and 1,000 sample Monte Carlo with global plus local, which is a mismatch. The devices are fairly big, so the difference is not that great. I'm going to show you a subset of the results here. Oh, this is the circuit, sorry. So there are 47 transistors. It's a differential. This is the input cascoded pair. That's the output pair of devices. That's the RC compensation Miller feedback. And that's the common mode feedback for the circuit. And it's hard to look at. So it is a real circuit though. So this is looking at the phase margin. What's being shown here is that the PDFs are kernel density estimates of from the Monte Carlo simulations. The pinkish thing in the middle is the extreme values that I get from running just the MOS best and worst case files. The purple lines are what I get from the capacitance low-high case, and the red lines are what I get from all of the extremes of combining all of the MOS R and C corners, which is 81 simulations. So phase margin is a fairly important thing. And the key thing here is that for this distribution, if I just ran MOS best and worst case corners, I would hideously underpredict the variability of that circuit. And if I just ran every corner I possibly could, I would be significantly over-predicting what that variation is. So the corners don't do a good job of predicting the variation for this parameter. This is slew rate for the amplifier, which is an important measure. You can see that actually the capacitances sort of don't too bad predict the variation of from the Monte Carlo simulation. But given that it should be ion C, what this has really surprised me was that it's only weakly sensitive to the MOS corners. I would have thought the drive current of the MOSFETs would have been significant for this. The one that really surprised me was IP3, which is a measure of distortion. It tells you when you start getting significant third harmonic distortion in the output of the amplifier. So it's distortion. So those capacitors are linear. The only non-linear element in the circuit is the MOS transistors. The resistors are very close to linear, much more linear than the MOSFETs. So it really is only the MOSFETs that contribute the nonlinearity. And you can see it's the variation in the MOS corners is incredibly underpredicts what the variability in the distortion level is. This was a really big surprise to me. So the takeaways from this really are that digital corners don't work for analog, okay? And as I said, it's not surprising because the sensitivities vary for everything that you look at, for every geometry, for every bias. So they shouldn't work, and they don't. Running the MOS RC corners is also inaccurate. Generally, it overestimates the spread, which a conservative designer would say, that's fine, I'll design to that. But if you do that, you throw away area, which means your part goes up in cost, or you throw away current. Typically, improving performance involves area and current for these types of circuits. So you're leaving something on the table for doing that. And the key thing here is that how much you overpredict it isn't guaranteed. It's unquantifiable. The other interesting thing is when I compared the unity gain bandwidth simulations compared to what John Crick had done for his topology circuit and the models that he had, which he didn't actually show, his MOS corners had actually overpredicted the unity gain bandwidth. And when I ran these, it actually underpredicted it. So whether it was over or under is not even determinable. And the upshot from this is that you really have to use Monte Carlo for analog figures of merit. The digital corners just aren't guaranteed to do anything. And you would be surprised how few people know that. The reason for doing this work was to present this internally at my company to the designers to try and educate them as to this. And the work was done, it was at CICC in 2013 for this, and we actually did it in collaboration with some data converter designers who are extremely good. Let me skip this example at the time. So I've been very negative about these corner models. So can you do something better? And the answer is yes, you can. If you think about it, what I'm showing here is two process parameters, I and J. The ellipses are intended to show 1, 2, and 3 sigma yield bodies here. And superimposed on that, in the dashed lines, I'm trying to draw constant contours for some electrical performance EM. So if you think about that, what you'd really like to do for the corners is you would like to find the points on the 3 sigma, or whatever sigma you define, ellipse. You'd like to find the points on those that maximize and minimize the values of the variations in the parameters. So that becomes a constraint optimization problem specified here. This is the variance-covariance matrix, or the inverse of it for the parameters. And it turns out that that has an analytic solution. So it turns out that analytically, based on first-order variation, and there are people that have extended this to nonlinear variations, you can actually calculate upfront what the values of the parameters should be for those corners. And this is implemented in an internal design tool that we have, and it's called exact corners or something. There's an analysis that people can set up and run, and it would automatically generate this for them in the Cadence design kits. But the trouble is that if I run this on a circuit and it gives me those corners and I squirrel them away so that I can just resimulate with those corners, if I make significant changes in the circuit, if I change the topology, if I change the length, if I change the biases, those corners need to be regenerated. So one other thing to be aware of is the curse of dimensionality. So I had said earlier that historically people typically put plus or minus 3 sigma variations in parameters. So let's look at P1 and P2. So if I put 3 sigma in P1 and 3 sigma in P2, I actually end up at 3 square root 2 sigma probability in manufacturing space. And it turns out that if I do it for n quantities, that I actually blow that out by a square root of n. So if you think about an over-designed factor, by the time I get to 9 things that I'm varying, if I put plus 3 sigma in each of these, I end up at 3 times overestimating what the variation in my final thing should be, with the caveat again that without knowing the sensitivities, I don't really know what it is. That's only in the probability space. And note that this is not just for the number of parameters in the models. If I take TOX, VT, delta L, and do that, then I've got square root of 3 variation. But if I do the same thing for PMOS, and then if I've got resistors and capacitors and bipolars that my circuit is sensitive to, and I've got 3 sigma files, even in E's, for each of those things, if I then put in worst case models for each of those components, I continually blow out the amount of variation that I'm putting in, and really over-design the circuits. Over-design is good, particularly when you provide to automotive who are very sensitive to it, but it's very bad when you're competing with someone who has better design practices and can make smaller die that use less power. So this is, again, something that people don't typically know. So thank you for your attention. I'll just quickly summarize those two things. So the BPV procedure that I explained to you, it looks complex, and history has shown me that people struggle to understand it. It's actually really rather simple because it fudges the parameter statistics to force fit variations in the device performances. We have a single program that I wrote in the company that does this. You give it like an input file and a set of models, and you have to tell it what the parameters are, and you have to give it a program that simulates the electric performances, and this thing just runs, and then it spits out what the variances are. It'll tune the model in initially. It actually will subtract out mismatch variations if the mismatch models are in there. Remember I said variances add to fit the global variance. I've got to take the total variance that I get from my specification. I've got to subtract the mismatch off. So it'll run a mismatch simulation, generate the variances, subtract them off, tune the nominal in, and then it will calculate the sigmas from the BPV, and it'll calculate the n-sigs from the corners from specified values for each of the electrical performances. And it runs in several minutes. And then as soon as you get information that says that the targeting for the process is wrong or that the variances that you had specified are wrong, you update them, and in 5 minutes you've got a completely new set of models. It works extremely well. So it looks complex, but it's not. Again, we use it for mismatch. There's a separate program for mismatch, but the mathematical basis works the same from them. And I haven't really shown it here. Well, I guess I did in the example. I had NMOS and PMOS that I fitted together, but you can fit multiple devices. You can actually include circuits. So we often put ring oscillator data in there as well. I've specified nothing what the E's are. All they have to do is vary with the parameters. As I said, Infineon took this process and they generated parameters for the whole technology from the SGPC fab data. And I think they measured 176 quantities and implied it, and we're very happy. So it looks complex, but it's not. It's really actually quite easy. The best and worst case models aren't, because you can't hit the plus or minus 3 sigmas for every EM, but more importantly, because it depends on the sensitivity, so they're really application specific. So the best and the worst case models have been and continue to be widely used. They've been the mainstream of the industry for 30 years. But the issue is, for analog especially, you've got to understand the limitations. And I'll say it again, the fixed variations in the parameters guarantee nothing about the variations in the electric performances unless you know the sensitivities, and the sensitivities vary with everything that you look at. So thank you for your attention. You're probably wondering, whoa, what's that? If there are any questions, I'll happily entertain them.
Well, let's thank the speaker.
So I have a quick one. So the BPV approach is, if I understand correctly, is basically a statistical calibration.
Yep.
You have data, you have a model, you have parameters that you don't know, and you find the parameters that basically represent
Right.
the model. And some of the things that we have tried and people in the UQ business use is when they do calibration. So if your model is not great, what ends up happening is that your distributions of parameters are unrealistically wide to
Yep. represent
the variation in the data, just because your model has to be stretched to represent the data.
Yep.
And people then, a technique that I was wondering if you guys use is to have add to the model what's called a model discrepancy, some function that you feed that tries to compensate model the error in the model in a way that your parameters don't suffer from these extremely large variations if your models are inaccurate. So I was wondering whether you guys explored those type of things, whether they're important.
Yeah, so the answer is no. When I've found that situation, it's generally because there's a problem in the extraction of the SPICE model parameters. Often it'll be like VT as a function of L is doing this, and then it goes off a cliff. Right. Yeah. So what'll happen is, then if you put in too large variation, all hell breaks loose from that. And what we do then is basically go back and fix up the SPICE model from which we get the sensitivity. And the reason for doing that is that if any designer hits that in practice, it's going to be a disaster anyway, so that we fix that model up.
Thank you. Actually, due to my understanding, your thing is you have a target for the performance, then you try to fit that performance, right?
Yep.
So if the calculation, the simulation is not the same as your target, you need to tune some parameters. This tuning process is randomly based random, or you have some algorithm to tell the simulator which one we need to tune?
Yeah, so you tell it what the parameters are,
Yes.
and then you have to provide a simulation script that will take a model file with those values of the parameters, and it simulates and gives us output what the electrical performances are.
Yeah,
So
you compare that output with your target, right?
well, it's actually that's done for tuning like the typical case and the corner models. So a nonlinear optimization will then adjust the parameter values so that the targets match. But for the statistical characterization, from those, the outputs as a function of the inputs, we actually do perturbations on the inputs to generate the sensitivities and then analytically solve the equations.
Okay, so you actually do a lot of simulations, and you do to all the outputs.
Yeah,
and you
yeah.
generate
If you have 5 parameters, you have to do 6 simulations because it does a perturbation in each dimension for the parameters and then calculates the sensitivity. I didn't say this, but you notice that it's linear and things happen to be nonlinear. There is a nonlinear extension to this, but we don't actually use it in practice. And sometimes if things are too nonlinear, instead of simulating a value of a performance, the script does a Monte Carlo simulation and actually returns the variation calculated from Monte Carlo simulation. So we do statistical simulations or random simulations in that case, but mostly it's deterministic just to get the sensitivities.
Yeah, so after you get the sensitivity, then you apply that to your input. Then
Right.
you have another set of things, which is,
Well, once the sensitivities are based on a linear model. So with the assumption of a linear model, you then just directly calculate the variances. The only slight trick there is if there is a slight nonlinearity, the value of the sensitivity depends on the range of the perturbations that you apply to the parameter. And so we actually generate the sensitivity by going from -3 sigma to +3 sigma on each parameter. Okay? And what that means is that you have to provide an initial estimate of the sigma. Once you've calculated it, you might get a slight difference in the sensitivity. So that's what the iterative part of it is that I described before. And the reason for doing that is that if you push a parameter to a corner, to a ±3 sigma value, that's where simulation issues with the model parameters will show up. So extreme example is sometimes we find that some resistances that aren't observable will have a huge variation, huge. And so it means really we shouldn't be including them in the analysis. Let me give you something that's more appropriate. The non-ideal component of current in a bipolar transistor has a very large variation statistically, it does. So if I want to take a -3 sigma value from that, I actually get a negative number. And so the plus or minus 3 sigmas is to exercise each parameter over its full range to make sure that there aren't any other simulation issues that come from that. But it's deterministic but iterative in that the sigma varies with the actual perturbation range. I've probably confused you more with that answer.
I think maybe it's the thing that you get some simulation result, but the thing is you have some iteration, but it converts to some code, like minimum, but it's not the reality. It's not real for some process, right?
No, it'll converge to correct numbers, and correct meaning that they're consistent with the underlying SPICE model.
One more question here? Well, two. I'll take two.
Okay. Yeah, so I was just wondering, can you extend your whole framework to non-Gaussian statistics?
That's a good question, and the answer is that we actually do. So there are some quantities, sometimes it's parasitic series resistance, and the best example is that nonlinear, the non-ideal component of base current, which has a monstrously wide distribution, and physically it should have. What happens there is that they're better modelled by a log normal than a normal distribution, and what we do then is we put an exponential mapping in the model file. So rather than having p plus the variation or being multiplied by 1 plus the variation, we exponentiate that, which then converts the normal distribution for the parameters into a log normal distribution for the variables. And the main place where I think there are issues with the normal distribution is particularly for memory design. And the reason for that is if you look at data, what tends to happen is they have higher tails than you normally get from a Gaussian distribution, and at present we don't handle that. So the only thing that's non-Gaussian that we handle is log normal, but you don't explicitly tell it. You actually have to set up the model file so that it has the exponential mapping and it does that for you.
So I had a quick question about how this is used.
Yeah.
So what I thought was happening is that circuit designers basically tell you these are the performance limits that we need to adhere to. And then basically from your model, you can work out what parameters and how much they can vary so that you're within those limits. And then I thought the process was sort of you go back to the fab engineer and tell them, like, make sure that all of these are in spec. But you mentioned earlier that this isn't actually the way it is.
No. It's really, the spec comes the other way. The spec primarily comes from manufacturing. The models then, they're used to generate targets. We have a thing we call the CPL, which is a crucial parameter list, and it specifies what the values for all of those targets are. And then they feed into the models which feed into design. So design doesn't actually specify it. They will have input into the technology saying that if you don't get the matching below this level or if the variability of this is too big, we're not going to be able to use the process. But not as, it doesn't really factor into how the model's used. That data flow is manufacturing to specifications, which involves some discussions and thought as well. Then that flows into the models and that flows into the circuit simulations.
So your goal is basically to tell the designers, given the variations that the manufacturing line has given us, this is
correct.
The impact on the circuit.
Right. So when they run, we do provide corner models and continually have to educate people as to what the limitations are. More and more people are by default running Monte Carlo simulations, even though they're much more expensive. If you have to run a few hundred samples instead of 3 or 5 simulations, it's much more expensive to do it. But in the fine line geometry nodes, anyone doing analog design has basically resigned themselves to actually having to run Monte Carlo simulations. And so, yes, those models then feed in and are used as the basis for simulating those.
So let me ask one final
Yep.
question. So this was a very nice presentation. So do you consider this basically a solved problem, how to handle variations in circuit design, or
that is
big challenges that we're...
That is a very good question. Statistical modelling is like Verilog A. Everyone reads one paper on it and thinks they're an expert in it. So I continue to see people that come up with improved techniques for doing models and statistical simulations. And in 20 years, maybe it's an NIH thing, but I've yet to see anything that would cause me to change from doing this. I've never seen anything that I think is better. On the analysis side, for things like the memories, they've got techniques that use the models, like high sigma Monte Carlo, that are necessary for that. The one thing that I didn't include here in variability in the modelling, I think is actually a bigger issue than this statistical variation. And I didn't mention it, and it's proximity effects, because everything's getting packed so closely together now that I can't consider my devices to be independent of each other. So as I bring the well edge in, or the STI in, or the poly spacing changes, or all this layout dependent stuff changes the variations in the device performances. And there has been and continues to be a lot of work in that area. And I guess as far as strict statistical variations, I have yet to see something that would cause me to change from this, although people still do continue to look at it. And I think the biggest issues are in the layout dependent effects side. And one of the reasons for that is these sort of analyses are generally simulated at the schematic level, often with extracted netlists for sort of parasitics verification. And so the whole paradigm of design has to change there, because by definition you don't know the layout dependent effects until you've got a layout. So you can't do an abstraction in your design at the schematic level if it critically depends on the layout. So I think the layout dependent effects are more significant in terms of needing continued work.
Okay, well, thank you again. You're warmed up now to spend
Yep.
teaching us about compact modeling.
Yep.
Let's thank Colin.
Thank you for your attention.